Hello, I'm David Weeks, and welcome to the first episode of Real World SF50 Flying. I've been flying professionally for over 50 years, starting as a CFI. Then I flew freight and light twins. I spent time as an air ambulance pilot in a Swearingen Metro and worked as a demonstration pilot for the Learjet factory. I had a 35-year airline career flying the 737-200 and 300, the A320 series, and I retired as a Boeing 787 captain. I've got over 650 hours in the SF50, and I like to share my Vision Jet experiences with you. This is the first episode of SF50 Real World Flying, and it's called Plan Your Flight and Fly Your Plane. Now, there may be other YouTube channels that have glitzier production values than this one. I like to spend my time writing and teaching about the SF50 and not doing post-production work. So just imagine that this video is like a hangar chat session between friends. If you want to follow along when I have approach plates or charts on screen, I'll provide links to them in the show notes. Let's discuss pre-flight planning for the SF50. I'm going to cover some topics that you may or may not have considered if your previous experience has been in piston-powered singles or light twins. Right off, I want to state clearly that the procedures in the Cirrus Vision Jet airplane flight manual are always controlling. This video is not flight instruction. Flight planning a Vision Jet is not like flight planning a Cessna 172. While it's almost as easy to fly as a 172, the Vision Jet flies fast and high. Most flights are IFR, and many are into busy airports. There are lots of things to consider, including fuel, payload, runway requirements, obstacles on departure, SIDS and stars, and how en route weather may affect your planning. Landing performance and alternate airport selection can be more complex. First, as pilot in command, you need to decide what's the mission. You need to balance payload versus range versus fuel required versus required performance. Payload. Is payload more important or the fuel needed for a non-stop flight more important? Like all aircraft, the SF50 design is a set of trade-offs. You can't carry full fuel and maximum payload at the same time. The plane will go further at long-range cruise speed than at max continuous thrust speed, but that's a significant decrease in cruising speed and an increase in flight time. Flying at long-range cruise also adds to the total cost of the flight, as we'll discuss later. So, why use long-range cruise at all? One of the best reasons to slow down is to be able to overfly an area of bad weather. Not only will you have to avoid having to shoot an instrument approach or dodge convective weather in the terminal area, you may not need to plan for an alternate airport and then have another problem with needing significant fuel to get to that alternate. Flying slower may eliminate the en route stop problem altogether. Also, on a long flight, you can get even more benefits from a tailwind by slowing down your cruise speed and thus reducing your fuel burn. Let the tailwind keep your ground speed up and you can fly even further than normal. In a headwind, do not slow down, as this merely increases the effect of the headwind. It now becomes a greater proportion of your now slower cruise speed. IFR or VFR? While the great majority of SF50 flights will be IFR and fly at or above flight level 180, there may be good reasons to fly shorter flights VFR. You may be able to safely avoid circuitous IFR routings and ATC delays if you can safely proceed VFR. Flying low may allow you to avoid icing or very strong headwinds at higher altitudes. When I fly VFR on legs of 125 miles or less, I sometimes fly the SF50 at 185 knots indicated with a power setting that burns about 60 gallons an hour. That produces a true airspeed of about 210 to 215 knots. A 125-mile flight at 12,500 or 11,500 MSL takes about 40 minutes and will use roughly 45 gallons, including taxi fuel. Flying the same leg at max continuous thrust takes 32 minutes, but will burn 49 gallons, including taxi fuel. So flying more slowly does increase the total cost of the flight a bit, as we will discuss below. For IFR flights, let's quickly review reserve fuel requirements from the SF50 standpoint. Now, every Vision Jet pilot has an incident rating, so you should be familiar with the IFR alternate airport and fuel reserve requirements. The issue for this discussion is how you wish to calculate the fuel burn to your alternate airport if one is needed. Now, if you use a ForeFlight performance account for flight planning, you need to be aware of how ForeFlight calculates the fuel burn to the filed alternate airport. Here's the URL of the ForeFlight document explaining their alternate airport fuel calculations. In ForeFlight, the time to fly to the alternate airport is based on a direct route from your destination airport to the alternate using the same performance profile as the rest of the flight and a cruise altitude appropriate to the distance to the alternate. The altitude to the alternate airport is automatically determined by evaluating the flight's cruise altitude, aircraft performance, and distance to the alternate. But where do you see the alternate for the altitude for the leg to the alternate? You can find that only in the navigation log. This is also where you can see how ForeFlight allocates the fuel for the instrument approach at the alternate. To account for missed approach, potential holding, and another instrument approach, a fuel buffer is automatically added. Buffer fuel varies by aircraft type and is added to the fuel required to fly direct to the alternate airport. Jet aircraft have 5 minutes of buffer fuel added for holding and enough fuel to fly an additional 30 nautical miles. Another popular application for flight planning is Vision ProFlight. It uses a much simpler rule for alternate fuel planning. It plans a straight line to the alternate, assuming 200 knots indicated and 70 gallons per hour fuel consumption. Vision ProFlight assumes less of a buffer than ForeFlight does. It's up to you as a pilot in command to account for ATC delays, routings, and weather when determining your alternate fuel requirement. The ForeFlight algorithm is considerably more conservative, and you may prefer it in busy terminal areas where you can't count on going direct to your alternate. Vision ProFlight may be preferable in less congested areas where you are more likely to be cleared direct to your alternate, and you don't need all the buffer fuel that ForeFlight includes. Let's talk about what I call cross-country approaches. Many of us are used to radar vectors to intercept the final approach course just outside the final approach fix without having to fly too many extra miles. But what if your destination or alternate is an airport like Kingman, Arizona, KIGM? While you may not have to shoot a VOR approach like this one all that often, consider the mileage and fuel burn needed above and beyond a direct approach to the airport in good weather. If you're coming from the south and are cleared direct Kingman and are cleared for the approach, you have to fly roughly 20 miles from the VOR, then do the procedure turn, which will take about 6 to 8 more miles, then fly back 20 miles to the airport. That's over 45 miles of flying. If you average 125 knots and 40 gallons per hour, that means you need 22 minutes and 18 gallons of gas to do the entire approach. Alternate airport minimums. Don't forget the 602 and 802 rule for precision versus non-precision approach weather at your alternate. But your desired alternate airport may have different weather requirements to be used as an alternate. Some airports, often found in mountainous terrain, have alternate minima that are quite a bit higher than standard. Bishop, California, KBIH, needs 2302 to be used as an alternate. So how do you know if your desired alternate airport has non-standard alternate minimums? If you use ForeFlight, search for the desired alternate airport, choose procedure, and choose any approach. FAA alternate minimums will appear to the right. What is normal cruising speed? FAR 91.167A3, the FAR that discusses alternate airport rules, says, quote, fly after that for 45 minutes at normal cruising speed, or for helicopters, and so on and so forth. Normal cruising speed is not defined. It could be the speed and fuel burn at max continuous thrust, or it could be the speed and fuel burn at long-range cruise. Does it mean that you have to plan flying with a power set at MCT, or can you plan to fly at a slow speed of, say, 120 knots? You get to pick. If your alternate airport is just a few miles away, you may safely plan on moseying over to using a slow speed and low fuel flow. If you need to fly a good ways, it may be more prudent to plan a higher altitude and faster speed due to the longer leg length. The SF50 can cruise at 180 knots and 50 to 60 gallons an hour. 45 minutes at that fuel would be about 38 gallons. But more SF50 pilots would be comfortable with 60 gallons as their 45-minute fuel, and some use 70. Don't forget to consider taxi fuel burn when flight planning. The SF50 burns roughly 12 gallons per hour at ground idle. That means a 20-minute taxi burns 4 gallons, a 30-minute taxi burns 6 gallons. With running the checklist and doing the takeoff briefing, it's hard to get off the ground in less than 10 minutes from engine start. So I think the lowest taxi burn would be about 2 gallons. But as they say, wait, there's more. We know the desired payload, destination airport, and required fuel load, but can you depart with the required fuel and desired payload, both safely and legally? Unlike flight planning for smaller general aviation aircraft, the SF50 has several weight-related constraints we need to take into account. Remember when doing your weight and balance calculations that the SF50's BOW, the basic operating weight, includes only the 2 front seats. Remember to add the weight for middle seats, console, aft adult center seat, and aft kiddie seats as needed. Don't forget to include the weight of a flyaway kit if you carry one, and to add TKS fluid weight. Per the AFM, a minimum of 1 gallon of TKS is required for all flights, even those conducted 100% in visual conditions. But you also need enough TKS fluid to run the system continuously when in icing conditions. Why? Well, the Williams FJ33 engine mounted on top of the fuselage would not be happy ingesting ice that comes off the radome, then over the windshield, and then into the engine inlet. While you would never want to cruise in moderate icing conditions, if you do plan to cruise in light icing, you need to have sufficient TKS fluid on board for the entire duration of flight in icing. Max takeoff weight is determined by the lesser of the MZFW, the MRW, the MTOW, the MLDW, and any climb gradient requirements for the departure airport. Now, that's a bunch of acronyms, so let's look at them one by one. MZFW, it's the maximum zero fuel weight. This is the maximum weight allowed with no fuel included. It's the actual basic operating weight plus the total weight of all the occupants and baggage and supplies. It's 4,900 pounds for the Vision Jet. If you do load the plane to the 4,900 pound max zero fuel weight, you have only 1,100 pounds left for fuel. That's 165 gallons. Subtract 65 gallons for reserve fuel, and this means that you have only 100 gallons for the flight. If you assume 70 gallons the first hour, you can see that you're not going very far. MRW, the maximum ramp weight, is 6,040 pounds. This is the heaviest weight at which you may taxi the SF50. If you taxi out at the maximum ramp weight, you must burn 40 pounds of fuel for taxi to reach the maximum takeoff weight of 6,000 pounds. 40 pounds of Jet A is 6 gallons. That's roughly a 30-minute taxi. This does allow you to plan for a long taxi time and still actually depart at the maximum takeoff weight. The MTOW, the maximum takeoff weight, this is the maximum weight at which you can begin a takeoff. The AFM defines this as the maximum weight approved for the start of the takeoff run. You don't start the takeoff run until you advance the thrust lever for takeoff. A line-up and weight clearance does not trigger the start of the takeoff run. The maximum takeoff weight is 6,000 pounds for the Vision Jet. If you take off at 6,000 pounds and are planning to land at the maximum landing weight of 5,550 pounds, it means a fuel burn of 450 pounds, which is 68 gallons. That's roughly a 1 hour flight. Be aware that an overweight landing now requires a maintenance inspection. The MLDW, the maximum landing weight. So we said this is a structural limit of 5,550 pounds. However, it's important to know that your maximum landing weight may be much less than 5,550 pounds depending on the landing airport density altitude. FAR 23.2120 prescribes a minimum climb gradient for go-around or balk landing performance. The FAR says, quote, for a balk landing, a climb gradient of 3% without creating undue pilot workload with the landing gear extended and flaps in the landing configuration. At high density altitude, the SF50 cannot meet this climb gradient with flaps set to 100% for landing unless the landing weight is relatively light. So, Cirrus provides landing climb performance charts to determine when flaps 50% is required to satisfy the 3% balk landing climb gradient at higher landing weights. For example, Flagstaff, Arizona. The airport is at 7,014 feet MSL, so let's call it 7,000 feet. To land at the maximum structural landing weight of 5,550 pounds with flaps 100% in a G1 or a straight G2, not a plus, the temperature cannot exceed 20 degrees Celsius or 68 degrees Fahrenheit, even though the runway is 8,800 feet long. The landing distance is not the issue. It's the go-around climb gradient with flaps 100%. If we use flaps 50% at Flagstaff, we can land at 5,550 pounds at 40 degrees Celsius or 104 degrees Fahrenheit. And to my knowledge, Flagstaff has never reached 40 degrees Celsius. For landing at max landing weight of 5,550 pounds and at 20C, the flaps 50% restriction comes into effect at 3,000 foot pressure altitude. At 30C, 6,000 foot pressure altitude. So, if in doubt, check the charts or use Vision ProFlight. Runway requirements. We're Part 91 and single engine, so the calculations are easier than for a bigger jet. All you must have is to be airborne by the end of the runway. But I strongly recommend use the distance to clear a 50-foot obstacle as the minimum runway length. It's easy to match the book numbers for takeoff as opposed to landing. Use all the runway, hold the brakes, set toga, then let it roll and rotate at 85 knots. Now let's talk about required landing distance and wet and slippery runways. We all know and love how easy it is for the Vision Jet to land smoothly, especially with its trailing link landing gear. But we do not have anti-skid braking, so it's also very easy to flat spot a main gear tire due to excessive braking before there's much weight on the main gear. In my opinion, it's harder to match the book performance for landing than it is for takeoff. I'd also like to mention that for Part 121 air carrier flight planning on a dry runway, the FARs require stopping within 60% of the effective landing distance. That is a 40% safety margin. A wet runway adds another 15%. While as Part 91 pilots, we're not obligated to have more than the absolute minimum runway required. Again, I strongly encourage you to add a safety factor into your planned landing distance. Check the performance charts or use Vision ProFlight when the runway is shorter than 4,000 feet or wet, or especially both. Don't forget that en route or approach icing increases both approach speed and required landing distance. If you can't be sure that you have a clean wing, then you need to land with flaps 50% and the charts require extra speed. VREF for an ice-contaminated aircraft is 115 knots indicated at max landing weight. That is 30 knots faster than the normal 85 knot indicated, flaps 100% VREF for 5,550 pounds. Now, using the classic formula that says energy equals 1/2 the mass times the square of the velocity, that extra speed converts to 83% more energy for the brakes to absorb. The landing distance for a normal 85 knot indicated VREF at max landing weight at sea level and 0 Celsius over a 50-foot obstacle is 2,430 feet. A max landing weight landing with an ice contaminated VREF of 115 knots at sea level and 0 Celsius requires 4,481 feet over a 50-foot obstacle. That is 85% more distance. Now, please do not raise the flaps after touchdown. The pilot's information manual says it takes 10 seconds to go from flaps 100% to 50%, and another 10 seconds to go from 50% to up. If you are already braking hard, you'll be slow way before the flaps have come up much. No air carrier that I'm aware of even permits raising the flaps before clearing the runway. There have been SF50 accidents where the PIC raised the gear lever just after touchdown, perhaps thinking he was raising the flaps. There was not enough weight on the weight on wheel switches to make the plane think it was on the ground, so the gear began to retract. But yet again, wait, there is still more that may restrict your takeoff weight. Climb gradients from mountainous airports. An excellent example of a demanding climb gradient is a departure from Aspen, K-A-S-E. Let's take a quick look. First, let me say that doing a climb gradient calculation with the AFM performance charts is difficult, tedious, and I think error-prone to say the least. Vision ProFlight has the ability to calculate and display the climb performance much more easily. The Aspen 7 departure requires a climb gradient of 650 feet per nautical mile to 13,000 feet MSO. ATC needs 840 feet per mile to 16,000. The gradient to rate table shows that the 650 feet per mile is equivalent to a no-wind rate of climb of 1,625 feet per minute at a ground speed of 150 knots. The problem is finding out what the Vision Jet will actually do. Now, we've got a 5-minute limit on toga power. We have charts for climb gradient with gear up and flaps 50%. We also have charts for the en route climb gradient configuration of max continuous thrust, flaps up, and 120 knots indicated. We would need to convert indicated airspeed to true airspeed and then do our best to account for headwind or tailwind. That's a lot of pencil pushing. Vision ProFlight shows that at 6,000 pounds MTOW and 0 Celsius, the SF50 can climb at 599 feet per mile, just short of the required 650 feet per mile gradient to 13,000 feet. We're nowhere near able to comply with the ATC requirement of 850 feet per mile. So, we need to reduce our takeoff weight. A reduction of 16 gallons or 109 pounds shows that we can meet the 650 foot per mile gradient at 13,000 feet. Naturally, we need to go back and check that we can still meet all the planned fuel needs we have with this reduction in fuel load. To get 850 feet per mile to 16,000, the takeoff weight needs to be less than 4,700 pounds or so. Engine anti-ice requirements make climb performance a bit worse due to the bleed air used to heat the engine intake. Just make sure you take that into account regardless of how you calculate climb gradient. It's important to note that the climb gradient tables on Jeppson SIDS reflect ground speed, not true airspeed. Adverse winds, tailwinds, aloft have a negative impact on the ability to actually make the climb gradient. Headwinds help the gradient. The non-plus G2 Vision Jet is, in my opinion, a slow climber. Here's one technique to maximize your climb gradient while not exceeding any AFM engine limitations. We know the AFM limitation of 5 minutes for takeoff thrust. While most pilots on most takeoffs reduce power to MCT after a minute or two, it is perfectly legal and safe to stay at toga for longer. One technique is this. When you decide to begin your takeoff, start the timer on the PFD. Set toga power. Climb at the 91 knot indicated best angle of climb speed for gear up and flaps 50% until 4 minutes has elapsed. Then reduce the pitch attitude, accelerate, raise the flaps, and reduce power to max continuous thrust before 5 minutes has elapsed. Now, don't forget that while the best angle of climb speed is 91 indicated with gear up and flaps 50%, the minimum speed for autopilot engagement with flaps 50% is 95 knots. So you need to hand fly until you're at 95 knots indicated or faster. What if there's icing in the clouds? Good SF50 pilots know that the minimum speed in icing is 160 knots indicated. So how do you climb out in icing conditions at the en route best gradient climb speed of 120 knots indicated? The AFM has an exception to the minimum 160 knot speed. A footnote on AFM page 2-26 that refers to the 160 knot indicated icing speed says, quote, excluding climbs, approach, and landing. Be aware the AFM does not allow flight in RVSM airspace, that's reduced vertical separation minimum airspace, flight above flight level 280, when the de-icing boots are in use due to the altitude phugoid that occurs when the wing boots cycle. See page 3A-18 of the AFM. However, you may ask ATC to stay in RVSM airspace, and ATC may grant the request. It is totally up to the controller. There are often climb requirements for SIDs that are not related to terrain. Let's look at the Las Vegas Gidget 2 departure. Some minimum altitudes are for traffic separation, not terrain clearance. You need to carefully plan ahead to make sure you can make all the restrictions, not just the close-in one. We can see here that the Tatia waypoint has an at or above 14,000 foot altitude restriction. Tatia is approximately 40 flying miles from the departure end of runways 19 right and left and runways 26 right and left. That's a considerable distance, and the winds may change significantly during your climb out. You also have to transition from best angle of climb in the takeoff configuration to either the en route best angle of climb configuration or the standard FMS mode climb speed. With all these issues to consider, can you actually get to 14,000 feet before Tatea? The G3000 will do a VNAV climb, but it cannot make the airplane do the impossible as far as complying with an at or above crossing restriction. If the current vertical speed is insufficient to make the target altitude, the unable VNAV altitude system message will be shown. If this message comes up, what can you do? If you've been climbing with the auto throttle set in FMS mode, you may elect to switch to manual mode and then adjust the desired airspeed to a slower speed to increase the rate of climb. Don't slow below 120 knots indicated, as that's the best angle of climb speed in the clean configuration. Yes, we may be slower than the best rate of climb speed, but when we have to cross a fix at or above a certain altitude in a given distance over the ground, it's the climb gradient we're concerned with. As always, if you think you're going to have a problem making a restriction, tell ATC ASAP. Don't wait until you're a mile from the fix and 800 feet too low to let the controller know you can't make it. Separation from other aircraft may very well be jeopardized. Speed versus fuel burn versus cost. I mentioned earlier that it costs more to fly slow. Let me add some detail to that. Every SF50 owner I know is on Jetstream, and the owner buys a contract for a fixed number of TAC hours from Cirrus. Let's assume that in January 2024, you paid $121,900 for 200 hours. That's $609.50 per TAC hour. It's also $10.15 per minute. Now, let's assume that your average price per gallon of Jet A is $5.50. If your average fuel burn is 70 gallons per hour, you burn $385 per hour of fuel, or $6.41 per minute of fuel. From those two numbers, $10.15 per minute for Jetstream and $6.41 per minute for fuel, you can instantly see that 1 minute of Jetstream costs much more than 1 minute of fuel. If you slow down to save fuel, it's going to cost you more in Jetstream time. Now, if slowing down does make a non-stop flight possible, as opposed to having to make a fuel stop, especially in IFR conditions, it may very well be worth it to slow down. The cheaper the fuel is, the less of a factor it becomes in your operating cost. If jet fuel costs you more per minute than Jetstream, then flying more slowly would be the smart move in terms of saving money. All right, let's recap what we discussed. Payload or range. Define your mission priority. Watch all your limiting weights, not just max gross weight. Be aware of the climb limited landing weight when your destination or alternate airport is hot and high. If you have to land on a wet runway or a runway when you have ice on the airplane, landing distances can be very long, and climb gradients can be demanding, especially in icing conditions. That's it for this episode of SF50 Real World Flying. I hope you learned some things that will help you plan your flight and fly your plan. I'm David Weeks, and thanks for watching.